Okay, sir.
Sir, should I start?
Okay.
Sir, whether my voice is audible to you?
Yes, yes. What about me?
Fine, sir. Good morning, ladies and gentlemen. On behalf of Balaji Group of Institutions, I would like to welcome today's guest speaker, Dr. V. Rajagopal Garu, for the fourth day of online faculty development program on recent advancements in power electronics and power conversion for distributed generation, organized by the Department of Tribly, Balaji Institute of Technology and Science. I feel privileged to give a brief note on today's honorable speaker, Dr. V. Rajagopal Reddy Garu. Sir completed his graduation from Institute of Engineers the year of 1999 and MTech in Power Electronics and Drives from Uttar Pradesh Technical University in the year of 2004. Sir received his doctoral degree from IIT Delhi in the year of 2012. Sir has 23 years of teaching experience and Sir worked as assistant professor in the Department of Tripoli Mallareddy Engineering College from 2005 to 2006. Sir worked as senior assistant professor from 2006 to 7 in Padma Shri Dr. B.V. Raju Institute of Technology, Narsapur. Sir worked as assistant professor from 2007 to 8 in SR Engineering College and Sir worked as research scholar from 2008 to 2011 in IIT Delhi. Sir worked as associate professor from 2011 to 12 in KITS Warangal and now Sir is working as professor in the Department of Tripoli Kakatiya Institute of Technology and Science, Warangal. While coming to the technical publications, Sir till now published about 18 papers in the reputed journals, and Sir attended about 34 various national and international conferences organized by reputed institutions in India and industries. Sir presently acting as supervisor for 5 research scholars in various reputed institutions across India. Sir also received an Indian patent on Hydro System 345 by DEL 2013 dated 7th February 2013 in association with one of the pillar of strength of electrical engineering in India, uh, respected Beam Singh sir. Sir received Fellow of IE with F122532. With immense pleasure and huge respect, I would like to hand over the session to today's speaker, Dr. V. Rajagopal sir. Sir, over to you.
So, thank you very much, Sri Garu. Thank you.
Thank you.
So, good morning, everybody. So today's topic, whatever we are taking, today's topic is so reduce switch technique for a solar PV system based multi-level inverter for PQ incrementer. So the agenda is also divided into two basic categories. First is the solar system. Then we are talking about the multi-level inverters. So multi-level inverters, basically we talk about the three basic categories. So flying capacitor, diode clamp, and cascaded multi-level. But here we are not talking about any of these things. We are talking about a new technology called reduce switch. In all these technologies, whatever we spoke, we have a large number of switches which are operating, that is power electronics devices which are operating. But here we are only operating with only 10 devices and getting a very good sinusoidal waveform from that. That's where we are talking about. So first part we'll talk about the solar system. Why solar we are using nowadays? What is everywhere? If I install a solar panel in our home also, if I could have 10 switches, I can generate a sinusoidal wave. That is the agenda. So first time when what is it's a necessity to go for this topic. When I visited one of the engineering college in Nellore, one of the BTech student has taken a 6-switch, I would say, multi-level inverter, and he was trying out to get a sinusoidal waveform. Then later I could see a, say, paper which was brought by one of the faculty in our institution. So there we started to work on this paper. Earlier I was not even working on, let's say, any multi-level inverter, nor on the solar systems also. So there the thing started. Later this I got this paper. We worked for 1 year, so we could implement this work at SVNIT hardware implementation. So we could publish in Berkeley Press this work that I'm going to present to you. So here, what is radio? First, we'll go with the solar. So which is so why we should think of solar? Why should we think of solar? Is increasing demand of energy. That's one thing. Day-to-day energy demand is increasing, and fossil fuels, that is the petrol, diesel, and other fuels, our prices are going up and up. So there is a demand for the renewable energy sources. And next is water. Whenever we talk about solar accounts for 52% of the prime energy input, basically in 2019, and it may increase up to 68% by 2050. That means that is the solar. So nowadays, everywhere, whenever we visit Hyderabad, some of the colonies, everywhere we have a lot of solar panels on the rooftops. So this topic belongs to electrical engineering. We are not going to study how the panels are made, what is the material used in the panels, what all the, we are just taking a ready-made panel and working on it. So we are only doing the application part. And these fossil fuels, whatever the fossil we are talking, day to day it is being exploited, and things we are thinking by 21st century, these things will not be there. So that's one thing. Whenever we are using this and connecting to the any of the loads, we require a sinusoidal waveform. So most of the inverters, it doesn't give any sinusoidal waveform. So this there comes our let's say work starts. So power quality issues are the thing we are working on it. Next is water. Main points. Reduce number of switches. So we are only operating at just simple 10 switches. And how much level we are going to get? 31 level. 31 level is 15 positive levels, 15 negative levels, and 0th level. That is basically plus 15, minus 15, and 0. 31 levels. And we are going to look into the power quality issues. What is the THD and all? So the results, basically the simulations are being conducted on MATLAB 2013B version environment. Those days, little long back. And hardware implementation is being done by Xilinx FPGA processor. Is basically RT Lab. So there is an RT Lab platform in SVNIT Surat. So there we have done that. So this is the thing. So whenever you look into the configuration, left side there are 4 switches, right side there we have 4 switches. The direction of the switches are different. I have chosen IGBT switches in this, and we have a top switch and one more switch on the bottom. So completely if you see S1, S2, S3, S4, S5 at the bottom, S6, S7, S8, S9, and S10 at the top. And we have 4 panels. We're looking into the 4 panels, V1, V2, V3, V4. This is the panel structure. But I have not shown before what is happening before this panel. This panel is not directly connected to the this multi-level inverter. This panel is connected through a DC-DC converter and given to the source. Basically, this diagram is not shown fully. This V1 is not. V1 is a regulated supply. So first we have a solar panel, then we have a DC-DC converter, maybe buck, and we are coming to a voltage here. So instead of showing everything, what we have shown is V1, V2, and V3, V4. V1 is of 10 volts, V2 is of 20 volts, V3 is of 50 volts, and V4 is of 100 volts. So whatever we do is in the combination of all these 4 only. For example, somebody want to get 10 volts level, I'll only use V1. And if I want 20 volts, I'll use V2. If I want 30 volts, I'll use V1 plus V2. That's the agenda. How we combine and all, we'll be thinking on this. These solar panels, whatever the supply is, 10 volts, 20, 50, and 100, is a regulated power supplies. We have to apply a MPPT algorithm for that. So this we'll be studying in the first part. Next part we'll be studying on the multi-level inverters. This is a combined diagram. First we'll attempt the solar things, then we'll attempt the multi-level things. So one by one we'll be understanding. So what are the solar cells doing? So solar convert light into small electrical output in milliwatts output. So each cell, if you just observe, it's very, very small and output is very small. So to get a useful output, you want a big output, a need of bank or array of cells are useful. Means to get, like example, I want 30 volts. I want this much amperes. How many panels you are connecting in series, how many panels you are connecting in parallel is the agenda here. The cost of the cells are high, but it's reducing. So whenever you look into any of the colleges installations, 50% or less than 50% government is funding, giving a subsidy, reduce, and nowadays the cell cost is also reducing because day-to-day materials improvement is also. So I worked on one of the project of Norway, which is in BV Raj Institute of Technology, where we for less period I worked, but I could understand so they are comparing two panels with the different materials they made, and that's the comparison they have been made. So efficiency of the cells is only 23%, but still it is improving. So whatever the efficiency, we are not interested. In India, lot of sunlight is there throughout the year, almost throughout the year, except in North India, if not in South India, we have a lot of sunlight. So even if I have 23%, 10% doesn't matter, whole output I should be able to convert. So that's why we requirement of MPPT algorithm is there. So here solar panels are situated on the rooftop of the building. So absorb heat from the radiation from sun and provides. So this can be directly, solar light can be directly used for domestic water heating also. But if not, we are using in, so anywhere. If I have been to Delhi, to many of the places, if you see everywhere on the house, we have a lot of nowadays. Um, we have panels which are like this, like an olden days construction, full panels. Even if water falls on this, it will just flow down and it will be cleaned. So cleaning is essential in a regular basis to get good output. That's one thing. And whenever you look into this everywhere, so when once we invest, I think we can take electricity for a much longer period if we maintain the solar panels in a regular mode. So here, Sardar Sarovar Narmada Nigam Limited, lot of panels are in Gujarat. Lot of panels are being put on the canals and all. We were thinking why it is being put on canals. Not only also what is a necessity. Also, we'll see many places they are putting on the river surface and some places on the canals. So to make the temperature of the panel in a limited zone. That's we'll be going to study in the coming slides. So terms related to solar panels, what are the why it is irradiance, watts per meter square. The amount of sunlight falling on the, so they'll say amount of useful sunlight falling on the solar panels. That's the thing. And whenever we talk about the temperature is very high. Temperature is high. The solar panel develops less power. That's the thing we are going to look into this. And what for wind speed is there? If wind speed is very good, wind speed is there, wind direction we are there, the temperature of the panel is automatically in the limited there. Like example, 25 degrees centigrade. If the temperature is there, then what happens? Automatically, uh, it will produce more solar energy. That's why irradiance, temperature, wind speed, and so whenever we look into these things, so we have what's a wind speed measurement in the solar panels wherever we see. So therefore, that's why we require that. So whenever we look into the IV curves of the solar panel, basically 3 points are very important in IV curve. The red line, whichever you see, is the IV curve. The blue curve, whichever you see, is the PV curve. Power versus voltage and current versus voltage. So if I take a panel and short circuit, put an ammeter in series, whatever the current I'll get, whatever the current I'll get from the solar panel is called the short circuit current, which is called ISC. So I take any of the panel, whatever the size it may be, so I put a short circuit across that. So what happens? It will draw current because there is no resistance, and this point is basically the short circuit current. And whenever you look into the other part, other side, the VOC. Whenever you open circuit the panel and check the voltage, open circuit the panel and check the voltage, whatever that point is called the open circuit voltage, which is called VOC. Between the ISC and VOC, if I keep on applying some more resistance or some load, the curve will start from ISC and go to VSC, or from VOC goes to ISC. Means if I put an open circuit and keep on applying the load slowly, what happens? Slowly the voltage starts reducing, and at one point, if I just generally short circuit, I'll get this one. Between this, if I plot whatever the voltage and whatever the current are there, if I multiply the DC quantities, if I multiply, I can get a curve which is in blue line, and this point, if I see the curve, it is like a hill. And it is like I'm climbing a hill, and at this point, it is at top of the hill. Again, I'm coming back down the hill. So this is called a hill curve. So most of the algorithms which we are using are hill climbing algorithms. Whether we take perturbed observe, or we take the incremental conductance, or we take some other algorithms. All the algorithms are only working on point where maximum power is obtained at this point. If you see here also on the red curve, the knee of the bent portion is basically where the maximum current and the maximum voltage is being achieved. And this point we are going to operate. Already the efficiency of the solar panel is very less. So now if I operate at some point here on the red line, some here or somewhere here, the max power is not maximum. So to operate at maximum power point, I require to operate here. To require to operate here, either I have to put a load which takes this much current, either I have to operate some, the converter in such a manner that the voltage is like this. So there are two chances for us. One is give a required current, take a required current, that is what, apply a resistance which is of required load. So if I have more resistance in my load circuit, the current will be less. If I go on reducing the load resistance, what happens to the current? Current is going to increase, because V is equal to I into R. If I keep the voltage constant, if I change the resistance, current can be adjusted. That's one way. If I keep the resistance constant, then what happens? If I change the current, or if I change the voltage, current can be automatic. Either of the two cases can be done. I have to either keep the voltage constant, either keep the current constant in both the cases. So what I'll do is we'll study both the cases one by one. We'll study both the cases. But my agenda of work is I have to only operate at maximum power point. This curve, if I'm looking at red curve, maybe at some irradiance. Some irradiance means what? Maybe at 1000 watts per meter square. But this may happen somewhere in 12 o'clock in the afternoon, if it is a sunny day. But whenever we talk about on cloudy day, immediately what happens? This curve may not look the same. The short circuiting point will be different. The VOC will be different. Automatically, the algorithm should understand where is the maximum power. Automatically, it should readjust. So we'll be studying that algorithm also in coming slides. So this point is not a constant point. It will be changing throughout the day, from morning 6 o'clock to evening 6 o'clock. Night there will be no sunlight. So that's the thing. First, what we'll do is what will happen if I change the irradiance? That's point one. And second point is what if temperatures are changing? What is the effect on the panels, voltage and current also will be studying. So here, whenever we are talking about this, first thing we'll be studying on IV curves and PV curves. First one is the IV curve of 1000 watts per meter square of some panel. We're talking about some panel. I'm saying that. So here, this is the 1000 watts per meter square. Second one is a curve for same panel for 800 watts per meter square, red one. Third one is 600 watts per meter square for this panel, and 200 watts per meter square is the fourth one. If you just observe, whenever the irradiance is large, generally we observe that the voltage generated is large. It is about 7.5 volts. It may be for a small panel we have choose to explain you. And whenever you look into, sorry, so 7.5 amps current is the thing. And whenever you look into the voltage of the black one is around 22 volts, a little less than 22 volts. And whenever you look into the 800 watts curve, 800 watts per meter square is the irradiance falling on the solar panel. The current is 6 amps, but the voltage is very near to the 22 volts. And in a similar manner, what is the general observation we do in the four curves? The whenever the irradiance is changing from morning, maybe 200 watts per meter square morning in the 7 o'clock sunlight to 12 to 1, that is 12 o'clock to 1 o'clock sunlight, that is watts, 1000 watts per meter square in a sunny day, then we see there is not much very difference in the voltages. The voltage is almost very near to 20 to 22 volts only. But whenever I look into the currents, it is dropping from 7.5 to even 1.5 amps. That means what? Irradiance is very much important to generation of more electricity, more current. That means automatically if you look into the PV curves on the right side, if you see the black curve is producing the maximum power at maybe 120 watts, approximately I'm saying 120 watts for some panel, and the red curve is doing around 100, blue curve around 75 or 80, and the last curve is only 20 watts. You just observe, if I am having different sunlights, what is happening? The voltages are merely changing, meagerly changing, but the currents are changing at the larger point. If I draw the right side of the curves from the left side curves, IV curves are PV curves are drawn from the IV curves only just by multiplication of voltage and current, and we draw it. The right side characteristics are being seen. So, what is the learning from this slide? If I have the irradiance changing, the current developed by the solar panel is changing drastically. That's the thing. Next ever, whenever we go to the IV curves and PV curves on the next slide, what have I attended? Now, in the previous one, I'm not touching any temperature. Here, basically what happens, temperatures and irradiance are changing simultaneously. But to make the reviewer, I will say, the reader understand or listener understand what is actually happening. Here I am doing the changing irradiance, keeping the temperature constant. We are not touching the temperature at all. Maybe 25 degrees centigrade all the time. But whenever you look into this, I'm not touching the irradiance. I'm only touching the temperatures. So we are operating this one in three different temperatures: 25 degrees centigrade, 50 degrees centigrade, 75 degrees centigrade, three different temperatures. So in somewhere, if I put a panel somewhere in Rajasthan and all, in summer, the temperatures may go very large due to the, let's say, heat of the sand, yeah, from the heat of the sun both. It may even go to 75 degrees centigrade also. And 50 degrees centigrade we can find in Telangana and Andhra also. So 25 degrees is almost a room temperature, I told you. So here if you observe the three curves, the curve which is with 25 degrees temperature is producing around 22 volts or little less than 22 volts. And whenever you talk about 50 degrees centigrade, the same panel is producing less than 90 degrees, 19 volts. And with 75 degrees, it is less than 18 volts. Here, whenever you observe, I'm not changing the irradiance. The irradiance is basically, maybe I am thinking of 1000 watts per meter square. Everywhere the ISE is same, almost the ISE is almost touching the same point, but the VOC is changing drastically. It's changing from one point to other point because of this step. That means what is the understanding? If the temperatures are very large, the generation of electricity in the solar panel is going to reduce. So we understood two things. What is the first thing is what? If the irradiance is going to change, keeping the temperature constant. So more irradiance, more power output. But whenever you look into the temperatures with the same irradiance, if I have more temperature, then we are going to generate less electricity. So if you just look at this, for the same irradiance, the temperature is 25 degrees, the maximum power 120 watts is being seen. With 50 degrees, it is around 110. With 75 degrees, it is around 95 watts, something like that. Approximately, we are talking about that. So the understanding is, so these two are not going to appear in two different times. It is going to appear simultaneously. Means when I put a panel in the sunlight, The irradiance is going to change, the temperatures are going to change. So it is going to happen. That's why wind speed, wind direction and temperature is very, very essential in solar power generation. So here the next one is what, IV curves. IV curves, what first we are going to think of, if I change the load resistance, I want to change the load current. So how, if whenever you look into your home, fan, tube lights, incandescent lamps, fridge, AC, TV, all are connected in parallel. They are not connected in series. They are connected in parallel. Every equipment in your home, single phase supply, we are connecting every resistance in parallel. Example, a resistance of the AC is, we are not talking about resistance, it's the impedance there. But if I just say the resistance of the AC is 20 ohms, and the resistance of TV, so generally we say impedance of the TV is 10 ohms. 20 ohms and 10 ohms are connected in parallel. Whenever I connect in parallel, what happens? The net effective resistance is going to reduce. 20 into 10 divided by 20 plus 10, effective resistance will be less than 10 ohms. So what happens whenever I apply many equipment in parallel, I'm only reducing the resistance value. Once I reduce the resistance value, the current is going to increase. So if I put more load, means what? If I switch on 10 tube lights in my home, indirectly what I'm doing, I'm reducing the resistance. Indirectly, I'm increasing the current, because the voltage is constant in the grid. So here, first case what we are going to study is, we are going to think of how to change the load. So I have selected three different resistances. One is a 0.0067. So we are only thinking of small panel. The panel output is 1.3 volts, 1.3 amps current, and voltage is around less than 0.6 volts. A panel, just we general study. So if I put a resistance load of this, what happens? This have a slope, resistance have a slope. It is touching these three curves. One is at, let's say this curve is at different irradiance. Current at 1 sun per amp, that is a 1800 or 600, means um, different irradiance we are talking about. These three curves are there. This will touch three curves at three different points. And whenever I take a resistance of 0.4 ohms, it is touching the top blue curve exactly at maximum power point, and other two curves not at the maximum power point. And whenever you look, if I look at the resistance here, the third line, if I take three different load resistances, if I take this 0.0067 ohms and 1.4 ohms is not touching any curve at a maximum power point, but 0.4 ohms resistance curve is touching the, let's say, IV curve at a maximum power point, but other two curves it is not touching at the maximum power point. That means what? What is the understanding from this curve? If I want to change the load resistance, load current, all the time I should vary the consumer load. Consumer load is what? Switch on some load, switch off some load, keep all the time at, so all the time. So what we'll do is, we'll do this with one more study also we'll do. Here there is a solar panel, the light is falling on that, so there is a generated voltage, and that is called VA, and I put a resistance R. The resistance is of 7.2 ohms, and the current which is taken drawn by it is IA. So what I'm doing, I'm not touching the voltage. Voltage is being kept at VA, but I'm changing the value of resistance. In this particular case, I will change the resistance to 7.2 ohms. So what happens? Keeping the voltage constant, the only term which can change is what? IA. And the red line is being drawn in IV curve for some panel which gives 90 volts and 5 ohm, 5 amps. It touches this curve at this point, and what is the power? 180 watts. This should have touched at knee point. This power would have been different. We'll study that also in the next slide. Example, if I change the resistance to 16.3 ohms, then I'll get a 372.8 watts. In the previous case, if I'm not operating at maximum power point, so the whole study, whatever I'm telling you in the slides, is to make you understand whether what is the difference between the maximum power and other than the maximum power. So if I have 180 watts, Now it is 372 watts. The power is almost more than the double. More than the double. Then more than the double means what is understanding? Operating at maximum power is very, very essential for us. And whenever you look into all the solar panel efficiency, it is less than 23% and around that. If I don't even operate at the maximum power point, then the efficiency will almost go to less than 50, less than 15%, 10%, and there is no use of using. So the job of the engineer or the researcher comes here. So we should always operate at maximum power. Now, if I am operating at 16.3 ohms, what is happening? That means what? I'm changing the load only. At this point, I'm changing the load. Then what happens? If I draw the IV curve or PV curve for this, the maximum power is around 372 is shown from the PV curve diagram. Now, the third thing is what? If I have 16.3 ohms for three different irradiance, same curve, one of the curve, I am saying this, don't look into the IV curves and all. So here, this is basically 5 amps current and 90 volts, this one. Whenever you, so what is happening if you observe, the voltages are reduced, currents are reducing. Why this is happening? Because in real life, the temperatures and irradiance are constantly changing. So this can be accommodated by saying that if the temperature is large, what happens? The temperature and if both are happening, neither this point is constant nor this point is constant. So if we have 1000 watts per meter square, 750 watts per meter square, 500 watts per meter square, if I take 16.3 ohms as the load resistance, for the top curve, if the irradiance is at exactly at 12 o'clock in the noon, then what happens? I'll generate a power of say 372 watt 0.8. But if the same curve is touching for 750 watts somewhere in the 10 o'clock time or 11 o'clock time, then the power generated is 235.62 watts. And the same resistance is being touched for 500 watts, maybe 9 o'clock in the morning in the sunny light, 119. Just observe, if I don't change the resistance of the load, three things are happening. If immediately sunlight is there, after some time there is a cloud, then what is going to happen? This line is touching at a different irradiance and different curve, which is not operating in maximum power point. If you draw the PV curves at the bottom also, you will observe that we have a different maximum power points. Then we'll go for the next. If what I'll do is, what is the motivation to take maximum power? First one is, if I want to operate for 1000 watts per meter square curve, I require 16.3 ohms. For 750 watts curve, I require 20.5 ohms. And for 500 watts curve, I require only 27 ohms. So what basically, why we are understanding this point? That means what? Somebody should be sitting at some place, changing the load all the time. That means what? If I want to operate at maximum power point, lot of solar panels are above my house. All the time, what I'll do? I'll understand the solar panel, maximum power point, understand, and switch off some lights, switch off some load, switch off some fridge, switch off some TV, or if I am inverting and taking. So that is not possible in real life. To change the resistance, change the currents, it's not at all possible. So if I want to operate in maximum power point, changing the resistance, load resistance, or changing the current doesn't make much sense for me. So here, if you just look at the right side of the curves, 75 degrees, this is the curve, 50 degrees, this is the curve, 25 degrees, this is the curve. Just observe the curves, to change in irradiance and this one, different things are happening here. So our motivation of this taking this topic is what? Putting a solar panel at the rooftop of our house takes some time, but operating at a maximum, understanding the operating point is this. So one case is been also said no to us. What is that? To operate at maximum power point, two things has to happen. Either I have to operate it with current, either I operate at some voltage. So some point where this knee point should be operating. It should be operating on the knee point. One case we have said no for that. That is the current case. Now we have to think of the voltage. So in our polytronics, we all know that changing voltages of a DC voltages can be only done by either buck boost or buck boost. So DC converters. So I'll be taking one of the example as a buck converter example I'll be taking. So what I'll be doing, there is a solar panel, a DC converter and a DC. So what we studied in our polytronics. So polytronics, what we studied, a chopper or a DC converter changes its DC voltage from a fixed DC voltage to variable DC voltage by use of one of the converter, maybe buck boost or buck boost. So it can be even operated in a PWM mode also by closed loop operation. So we can operate in maximum power point algorithm also we can operate. That's a basic idea. So here, so in all the DC converter, generally we use the buck converter or a boost converter or buck boost converter. We use MOSFETs. So MOSFETs can operate at the frequency of 100 kilohertz or more. Books are giving around 200 kilohertz also. So there's a, and the voltage is what the MOSFET can operate is little less. The voltage is, it is a low voltage device, maximum switching frequency. Whenever we take about the IGBT, which is shown in the figure, these IGBTs are basically operating at 20 kilohertz and medium power applications. The power will be medium, but the switching frequencies are around 20 kilohertz. Nowadays, SiC devices are coming, silicon carbide, gallium nitride. So here these are the devices which can operate at a maximum power and maximum frequency. So here, whenever we talk about these things, so here, whenever we are talking, if I want to use a thyristor, thyristor can only operate at 400 hertz, but very high voltages and very high currents. But in all the DC converters, the switching frequencies are around maybe 100 kilohertz. And even if you are operating at 20 kilohertz or so, that's very good. That's why I chose the IGBTs for the particular applications. Medium power applications, 20 kilohertz switching frequency. If I combine the IGBT with the diodes, the anti-parallel diode is always kept in parallel with this. With the IGBT arrow is downwards, the diode arrow will be the topwards. It is an anti-parallel diode. And this combined we generally what happens this one, if I give a gate pulse, the cathode and also emitter both also get to each other, means they get connected to the each other point. So this is a combination. IGBT is a combination of BJT plus MOSFET. So it's a voltage control device. So BJT is a current control device. So here, whenever we talk about the this one, in a buck converter, whenever you see, this is the solar panel, this is the load. If I want to change the voltage, what I'll do, when I switch on this one, the power, the current will go from here through this load inductance, to this load resistance, going back. Whenever I remove this, whenever I switch off this, this can be an IGBT, this can be an MOSFET, and this can be a SiC convert, silicon carbide device. So here, whenever we are talking about this, whenever I switch off, so this switching frequency should be on the very high side, maybe in the order of kilohertz, 20 kilohertz. So I cannot use GTU, I cannot use an thyristor. So I can has to go for BJT. I can go, but BJT is a current control device, having a disadvantage of let's say secondary breakdown and all. So generally we think of IGBTs and MOSFETs. So here, whenever I switch off this one, what is going to happen? The inductance stored in this one will be feeding through freewheeling action through this diode. So this diode, whatever we are using, we cannot use a diode which is a general purpose diode. Either we have to go for fast recovery diodes or Schottky diodes, so that the switching frequency of diode will also be very fast. So to operate with this particular device. So here what we are doing, whenever I am changing from a fixed voltage to a variable voltage. If I give 100 volts, the duty cycle is 40%, then the voltage whatever we get is 40 volts. That means what? I'm just talking about the buck converter. But this system is, what is this capacitor for? It will filter out whatever the voltage ripples are there in the load. It will filter out the capacitor, and whatever the current ripples are there in the load, this one are being filtered out by this one. This will make, if the inductance is very low, the load current will become discontinuous. If the inductance is large, this becomes continuous current. You all know that in the from the power electronics. So here, but this is not going to work for our application. So here a different. Here my voltage is fixed. Why the voltage is fixed? Because in my particular application, I need 10 volts, 20 volts, 50 volts, and 100 volts. Four different voltages. They are very fixed. Fixed means what? It should not change. And this is what, and the solar panel, whatever you are having, earlier the capacitor was on the AC side. Now I shifted to the solar side. Load side it was there, I shifted to the solar side. So what way, and diode is kept and this one is there, and whenever I switch on this one, my load voltage is not going to change, because the load voltage is a battery type thing or a capacitor thing which is fixed. So as soon as I switch on this switch, what is going to happen? This is not going to, or say, the voltage of this is not going to reduce, but solar panel voltage is going to reduce. You generally observe whenever we put a load on any of the solar panel, any of the system, the voltage drips or voltage drops. Whenever I remove this one, what is going to happen? The voltage is going to increase of the solar panel. Indirectly, what we are saying, the solar panel voltage where it should operate. If I operate the switch in the maximum power point thing, automatically what happens? The solar panel will be only working at that voltage which is at maximum power. So, and why should we keep this capacitor? So that whatever we are operating, exactly the solar panel voltage doesn't dip very fastly and come up very fastly. There is a small capacitor in the input side. So here, whenever we are looking into these things, we are not changing the load side voltage. We are changing the input side voltage. That's the solar panel voltage. The solar panel voltage is changed because of one thing, that is switch. If I operate the switch for more duty cycle, the solar panel voltage will trip for more time, go to the lowest level. If I don't operate the solar panel, the voltage will rise to a high level. That means what? The solar panel voltage can be adjusted. Earlier we tried saying that how can I adjust the thing to operate at maximum power point? I can only do two things. One is change the current, change the voltage. Current is not working out. Now this diagram shows changing the voltage. So we have studied a conventional buck converter. Conventional buck converter changes a fixed voltage to variable voltage, but this application change wants variable voltage to the fixed voltage. So what happens? The capacitor place has been changed. The switches are being moved ahead of that. So now if I want to operate, I need one algorithm to operate this switch, to generate the duty cycle, for the switches. Switches is what? It is an IGBT or a MOSFET. In our application, we are used an IGBT. Okay. So here, what is this? This is the maximum power point algorithm. So what is the understanding? Whenever I learned this one for the first time, I was thinking this is like an big thing where I cannot even learn it. And I learned this maybe after the age of 45 or 46, maybe 4 or 5 years before only. Before that, I was not even working on this. Maybe not even working on the MPPT algorithms and all. We were only working on other things and all, but I don't even know how to operate on this. So how to make? So whenever we are, this is algorithm which we generally say perturb and observe. So whenever I say incremental conductance based algorithm is the other algorithm, we worked on both the things. We have some more algorithms to work, but algorithm is what? A procedure. Somebody may, whenever I heard this same name during my MTech days, I was thinking algorithm means it is looking like a Chinese word, a Greek word. Then what is this happening? I was really puzzled also to understand what is actually happening. But here, whenever you look into this, what the basically, somebody raised the question. See this, sir? At the end of the session,
Sir, we'll try to permit the participant to raise the question at the end of the session.
Okay, so I'll give some time to the participants. At the end, whatever the things will be there, I'll try to, I'll say,
We'll try to address the queries.
no, I'll try to tell all the details of these things. Then you can even further, you have doubts, even I'll clear after the classwork. Okay.
Thank you.
So here, this is the perturb and observe. Perturb is what? Disturb. You disturb something. Observe is what? See. Look at that. So this is the algorithm which is looking into that. The algorithm says first is what? Measure, sense the voltage. Sense which voltage? The panel voltage. VA, V and I. VK is what? Instant. Kth instant. Instant means that particular instant. Means 9 o'clock, 32 minutes, 50 second. Maybe something like that. So instant is what? Kth instant. Generally we say N, but whenever we are putting the same algorithm into the publication, we are getting plagiarism things. That's why we change it to the kth thing. So here, Srinivasan sir, I'll attend. This you'll at the end of the session you'll be clearing your doubts. Okay, clearing your whatever the understanding you have. Okay, here I'll sense the voltage and current, and whenever I multiply, I'll get the power. Because DC1 directly can multiply, I'll get the power. So what I'll do, any processor or anything, whenever we are understanding this, there is a peak power in the k minus 1 instant and power in the k minus 1. How can you do in the system? So if I have two instances, if I put in one delay loop in this one, p minus p n minus 1, p n means nth instant, nth minus instant, or kth instant or kth minus instant. If I subtract, if I'll get a zero value, that means what? The previous value of power and this value of power is zero. Then what happens? You are at the highest point. When this is a flat portion. Flat portion means what? Where the power of the previous sample and power of the present sample are same. So what happens if I subtract both? The answer is zero. So I am working on the maximum power. No need to think. So yes, come back and here. No need to update the duty cycle. No need to update the duty cycle. Example, if I am saying the present instant is more than the previous instant, it's not zero. Then what happens? Not zero. It is not equal to zero. What happens? It is coming here. Means if it's not zero, means it's not operating at maximum power point. It will come down. Then I have to check whether this power and the previous power is positive or negative. Positive means what? I can be, if I have power here, if I am working here, but I don't know whether I am working going up the hill or going down the hill, because the PV curves look like a hill. And if I am operating here, left side of the hill, my present power, I am disturbing the power in the increased manner. Means I am disturb the power in the increasing voltage manner. So I disturb the power in increase, means I was operating at 90 volts. I disturbed it to the 91 volts, increased voltage manner. So what happens to the power? The previous power is less and the next power is large. Then what happens? This becomes positive. This becomes positive. That means what? If previous power is less than the present power, that means what? I'm climbing up the hill. I'm not climbing down the hill. If you look at the other side, if the disturbance is here, down the hill, the present power will be less than the previous power because I'm going down the hill. Then these things will have two things. From this rhombus, I'll understand whether I'm going up the hill or whether I'm going down the hill. If I'm going up the hill, S means we have to come this side. If I'm going down the hill, means I have come this side. But for the also listener to understand, so here what we do is first I'll take I'm going up the hill, and whenever I'm going up the hill, I'll come down here. Whether I have given the disturbance in the increased voltage direction or decreased voltage direction is very essential for us. I already told you I already told you that I disturbed from 90 volts to 91 volts. That disturbance is on the higher side. That means what? The instant of the voltage now and the instant of the voltage in the previous case is more than zero. That means what? S means what? I have to come down here. S means what? I'm come down. Now I understood that I'm going climbing up the hill. I need to increase my voltage reference. How I increase the voltage reference? V reference is equal to V reference plus C. Plus C is what? So a small increment called D. The duty cycle is being increased by a small value. Because I'm working on this point, I have to go up to the hill. That means what? Again, I increase the C. And what happens? Update and return. I'll come back here again. Then what happens? Again, I'll check the power. Again, I'll find that power is not at maximum power point. Again, I'll find that the power is more because I'm climbing up the hill. So yes, again the disturbance is what? Increasing sidewall because I added one more C value. So what happens again? I'll come back here. Then what happens? I am at this point all the time updating the reference value to a higher value. The voltage is being increased to a higher value. And at last, I climbed the hill and I'm at the top of the hill. I climbed the hill and I'm at the top of the hill. Then I'll sense the voltage. This value becomes zero and I'll come down here. I'll come down here. See how the things are happening. Now, this is the thing happening. Example, somebody may say, sir, I made a disturbance in reducing voltage direction. Means I'm here, I want to climb, I reduce, I'm at the down the hill, not on the up the hill, I'm on this side of the hill. Then what happens? I disturb the voltage in the negative direction, means reduce the voltage, reference voltage. Then what happens? Here, I take multiplication of voltage and current of the solar panel. So this power is not same. So this is not equal to zero. I'll come down here. Now I'm here means what? I'm coming up the hill. Up the hill means what? The voltage is reduced. Voltage is reduced. The previous sample power is less than the present sample. Then what happens? I'll come this side. Now the disturbance is what? The disturbance I made is reduced voltage. Reduced voltage is what? The previous sample voltage is more than the present sample. Now I don't have S here, but I have a no here. Then what happens? No here means I'll come here. Now I'll reduce the reference voltage to a less value by C. Then what happens? Slowly I'll update it. Again, I'll go back here. Slowly I'll come back to the maximum power point. So we have four things in these four things. One is S, we have increase and decrease. No, again we have increase and decrease. So whenever you go to this algorithm, even if you don't understand this algorithm, you just put a small thing. Again, I can take one more small session where you can understand this. So I have taken in this my MPPT algorithm only the right side one. Even if you understand this one also, that can be very easily explained. So this is the total MPPT algorithm. Why should we understand this? Is to operate at maximum power point. So to understand maximum power point, it is to change the voltage or change the current. Change the current is not possible because we have to change the consumer load. The changing the voltage is what? We have to use a buck converter. Conventional buck converter is not going to work. So we have to go for an modified buck converter that we have done and applying maximum power point and generate a duty cycle from this to operate the switch of the buck converter. That's the basic idea. So whenever you look into this, this is the maximum power point where we are operating. This is the maximum power point, and when we are operating maximum power point, this is the IM peak, the maximum value of peak. This one. So this is also something where we are maximum power point. So now in this total thing, I told you already, there is a division of two things in our study, whatever we are doing. We have a solar part, we have a multi-level part. Multi-level is what, not the conventional multi-level what we are using. The multi-level inverter is not a diode clamp multi-level inverter or a flying capacitor or a cascaded multi-level inverter. We are using a multi-level inverter. So all these multi-level inverter, whichever we study, that also we have put one, say one of the paper In cascaded multi-level also we have done some good work. But here what we are doing is this multi-level inverter is going to operate in less number of switches, and we are not going to use any PWM operation. We are going to use the fundamental switching operation, and we are making sure that for this, actually I have choose one MTech student from BB Raj Institute of Technology. Daily I used to tell him to draw a sine curve, so on a big paper, and one, or I can say on each point of the sine curve, what is the time we have used to think, and we have given the exact, let's say, the pulses, so that it is almost operating at a sinusoidal. End of the PPT, you will understand what is the actual things are happening. So here, what are harmonics basically? Whenever you understand the harmonics, what is it? Whenever we see an irregular waveform, so all the books like Rashid, Ned Mohan, or V.S. Bimra, or any of the Fourier analysis, whenever we are studying, we study Fourier analysis to, we study Fourier analysis, we study Fourier analysis just to, a periodic waveform can be say divided into many sinusoidal waveform of sine and cos curves, sine and cos curve added in a different amplitude and different places to get one waveform. So that example we are going to give. If I have a sinusoidal waveform here, if I add a third harmonic to this, which is 3 times the frequency, and having amplitude 1/3 of the fundamental frequency, then what is the waveform we are going to get? We are going to get a waveform. We are going to get a waveform like this. If I add a third harmonic and if I add a fundamental, I'll get. But for me, fundamental is essential. Harmonics are not essential. Means it's a unwanted things. If I add the fifth harmonic to this, if I add a fifth harmonic to this, what is going to happen? The next waveform, whatever we are going to get, is a waveform of this pattern, waveform which is of this pattern. And if I add one more, is I added a third, fifth, and now the seventh, which is 7 times the frequency of the fundamental, I'll get a waveform like this. And if I add a ninth harmonic to this, I'll get a waveform like this. If I go on adding such waveforms, at last I'll get a square waveform. So square waveform input, the output of a single phase inverter is a square waveform. The THD of such inverter is 48%. 48% THD means, according to IEEE 519 standards, the THD of any waveform, sinusoidal waveform, should be less than 5% of the THD. 5% of the THD is what? To keep all the motors. Example, you may ask me, sir, if I have more than 5%, 10%, 15%, or a sinusoidal waveform, or I can say square waveform given to a motor, what is going to happen? If I put some inverter in my home, and if I produce a single phase inverter with 4 switches, that is a cascaded one. If I use a simple bridge inverter, the whatever the output I'll get is a square wave inverter. So to understand this example, I was standing near a machine, a motor, whose currents were supplied in a harmonic manner. Harmonic currents were supplied. I was thinking that the sound of the motor was that horrible. Even I was unable to stand near the motor for some time, opening my ears. I had to close my ears. The sound was very, very like an aeroplane flying over the building. That what sound was coming from the machine. Sometimes I felt that the motor may come out of the base due to vibrations, and it may come out of the vibration, come where blast like that. That much is the sound coming from the motor. That means what? If I supply any currents, anything above 5% of the harmonic, which is allowable range, it is not good for the machine. What happens? A fundamental harmonic, a fundamental current may rotate the machine in the forward direction. Third harmonic may rotate in the reverse direction. Fifth may rotate in the positive direction. As a whole, machine will come into the vibration, and efficiency the machine will go down. We have to derate the machine. So which is we are not going to do that. So less harmonics is very, very important. Power quality improvement is very, very important for us. So here, before understanding this, to make you understand, everybody knows this, a small basics of this. Example, if I have some voltages connected like this, from X to Y, if I want VYX, Y is at higher potential, and if I connect the positive terminal here and negative, that is called VYX. What is happening? So how the voltages can be done? If I travel from X to Y, plus 10, plus 50, this is reverse, minus 20, plus 100. The voltage between VYX is 140 volts. That means what? Arrangement of voltages in proper manner gives us different voltage levels. That is the understanding here. Second one, if I connect like this, I want VXY. X is at higher potential, then what? I'll travel from Y minus 100, plus 20. This is basically minus 100, minus 20, minus 50, plus 10. The voltage will be minus 60 because I'm calculating the value of VXY. So VXY becomes a negative current. Why should we understand this? So next we'll go for this one. So in this one, I told you 4 voltages were there: V1, V2, V3, and V4. V1 is 10 volts, V2 is 20 volts, V3 is at 50 volts, V4 is at 100 volts. We have 4 different voltages. These 4 different voltages are coming from 4 different solar panels with MPPT algorithm and coming to this place. So to understand this, what I have done a fixed voltages, because we are already operating with solar panels. So voltage will be fixed. So these batteries or things will be fed from the solar panels through MPPT algorithm. So that the worry is already been done. Here, the first diagram. Whenever you look into the first diagram, I'll just go back and make you understand that. If I go to the first diagram, so I'll not take much of this. What I'll do is one diagram. If I make you understand, remaining is automatically understood. So here, whenever I look into this, okay, what I am doing? There are 10 switches. Voltage V1 is 10 volts, V2 is 20 volts, V3 is 50 volts, V4 is 100 volts. I want a current in this resistor. I only use the resistive load to go from positive to negative to get a positive waveform. Negative to positive means what? This side it should be positive, this side it should be negative. It is the negative direction of current, like this. But if I want to go from place like this point to this point, the current should be this way. It should be in this way. So here, to get this wave, the first level is 10 volts. 10 volts is what I have. V1 is 10 volts. So I connected the positive point. So I operated the switch S2 and I connected to this point. But negative should be connected to the other point. So what I should operate? I operated S4, S5. S5 is not operated, or there is a diode across it. S6, S7, and the minus. That means what? If I have this one, current will come like this, flows like this, goes back like this. That means what? The voltage across this resistor is 10 volts. To operate this, what are the switches we should operate? S2, S4, S5, S6, and S7. So out of the 10 switches, my pulses should go for only these switches. Remaining switches, no pulses should go on. Now I want the second one is 20 volts. 20 volts is where here it is reversely connected. V1 and V2 upper plates are positive. V2 and V4 upper plates are negative. Now I want the current should go only in this direction, but the voltage should be 20 volts. What I had done? This one positive, I operated S6, S5, S4, S3. So what happened? This thing has been connected here. Now the negative plate is being connected to S side to the negative side. Now what happens? The positive from the V2, 20 volts, S6, S5, S4, S3 through this resistor S8 going to the negative plate. Now to operate in 20 volts, what all the switches should be on? S6, S5, S4, S3, and S8. My understanding is it is not closed loop operation. We should give pulses to only this one. It's an open loop. Now I want the third one. I want 30 volts. What should I do? Now, to operate in 30 volts, V2 and V1 should be in series. Should be in series means what? The positive plate is connected to here, this point. This is only 10 volts. The negative plate is connected to this positive. Negative is connected through S4, through S5, S6 to the positive. That means what? V1 and V2 are in series. And negative is connected through S8 to the negative. So what happens? 10 plus 20 is 30 across this. So if I operate from here, what will happen? 10 volts positive, if you're going here like this, coming back like this, through 20 volts, coming back, it is 30 volts. Now comes, if I am operating this switch, I want 40 volts. If I go to the next slide, 40 volts, what will happen? If I go to the 40 volts direction, what is going to happen? What all the things should operate in this? Here, whenever you see this diagram, 40 volts. So what the positive should be connected here. So what they have done is, just observe the things. 40 is there. Where is this one? V3 is 50 volts. 50 volts is connected through, just if you observe, 50 positive is connected to S1, is connected to the positive. Positive is connected to positive means what? Both are in the opposite direction. 50 is in opposite to 10. 50 minus 10 is how much? 40. So here it comes like this. Through this goes back to the positive. Negative plate is going through this to the negative side. Whenever I operate this one, 50 minus 10 is going here through this resistor, coming back, going back to this. That means what? We are operating at 40 volts. If I want 50, what I'll do? Just I'll connect it positive to this side, negative to this side. So 50 volts is this. So everything what we have done in this one is we have operated all the things. So we could understand 10 volts is the voltage of V1, 20 volts is the voltage of V2, V3 is 50, V4 is 100. So we make a combination of all this. So what we have done, we have made 15 diagrams for positive level. So whenever you just look into the switching patterns, there are 10 switches. So whenever you want to operate, the output voltage is 0. What happens? If S1 is on, nothing is going to, the remaining all switches are off. There is no voltage. If I want to operate the switch level, then it's 10 volts level. S2, S4, S5, S6 should be on, and S7 also should be on to get V1. So I made a total as a last levels. The 15th level is coming as how much? V4 plus V3. V4 is 100, V3 is 50, it is 150 volts. In the similar manner, we have done, so I'll make you one understanding in this, how the return reverse voltage will go. So here, whenever I look into this basic visual diagram, whenever we look into this diagram, we'll just go to the 200 side. Negative voltage means what? Negative current. So what we'll do now here, this will not be any more positive. If you just observe, the 10 volts is connected through like this, like this, like this to this point. Positive is connected to this point, negative is connected to this point. Now what happens? Nowhere this is positive and this is negative, but this should go to this side and this should come to this side. What happens to the voltage? Now this voltage will become a negative current, because positive voltage is this place, negative voltage here. Automatically the current goes in the negative direction, so a negative 10 volts will come. In the similar manner we can do for the other voltage level. The similar manner you can do for the other voltage levels. So we have given for -10, -20, -30, -40, -50, -60, and -70, -80, -90, and here -100, -110, -120, and up to -150. So here also we have done all the levels, all the switching patterns. So here at last, whenever you take this one, this is the last one is -V3 -V4, -100 plus -50 is -150. We'll get a positive 15 levels, negative 15 levels. Zeroth level is when you're not operating anywhere, that is 31 level inverter. And this you are able to get only through 10 switches. Intelligently we are operating 10 switches, and we are able to get it. And we are even applying a solar energy through MPPT algorithm, DC-DC converter, to a fixed voltage. So voltages are not going to change, V1, V2, and V3, V4. So here this we have done in the simulation. So whenever you look into the simulation side and all, these are simple repeat sequence generators. Whenever you go to MATLAB and all, there is a small block called repeat sequence. In the repeat sequence, for a cycle of 0.02 milliseconds. 0.02 is why? Because 50 hertz is nothing but 1 by 50 is 20 milliseconds. 20 milliseconds is nothing but at the bottom you can see 0 to 0.02. Each switch, if you just observe the each switch, I'm operating for a different time, because I told from the two say tables, table 1 for 0 to 15 150 volts, and the table 2 for 0 to -150 volts. I'll operate these switches in such a manner that 0 to 1 or 0.01, this all the voltages are positive. From 0.01 to 0.02, all the voltages are negative. So as a whole, what is going to happen is we'll get a positive waveform and a negative waveform. When we done the simulations like this, I compared this one with a sinusoidal waveform. Whatever the waveform, stepped waveform. So the MTech student have worked on this to make understand only where the step should start, where the step should end. So I made that the sinusoidal waveform is only going through the center of the step, so that the top of the step will be exactly passing through this one. If whenever you agree with any given 10 level switches, you cannot get this smooth waveform where the THD is very, very less. The THD, you'll just look into the hardware part and simulation part also. The THD will be almost, I think, 1 to 2% only. Whenever you look into this, this we have done in the hardware on the DSO, digital storage oscilloscope. In digital storage oscilloscope, I cannot take 10 different readings at the same time. I can only take only 4 because it's a 4 channel. The available number of channels in any of the labs are only 4 channel. So we could only make you understand 4 channels for this basic understanding. So whenever we looked into this, in the hardware part also, whenever we are taken in the RT lab, we could understand almost a pure sinusoidal waveform, and the second pink waveform is basically the current waveform, because I'm taking the resistive load. So we could understand this, and whenever we done this waveform, the THD, the voltage is the fundamental voltage is around 106 volts. This is fundamental, not the total one, and the THD is around 1%. And the voltage is here also. If you just observe, frequency is 50, the current is 7 amps, the voltage is 106. Whenever you look into the current side, if I take in the current, this one, the current is 7.02 amps. THD is again 1% because I am only taking resistive load. How much is the power generated? Also, we have 4.66 kilowatts is the generated power. We took 4.79 kVA and 1.12 kVAR is the reactive power. This reactive power is because the amount of say the power factor is 0.97, because completely the THD is not equal to 0. So because of that, we have little reactive power and active power also. Active power is larger, reactive power is less because of this. And at the end, we want to conclude this. Whenever we want to conclude, a prototype of reduced switch multi-level indoor photosynthesis has been implemented, and the THD is according to IEEE 519 standards. And it has been observed that reduced switch multi-level inverter results are highly satisfactory. And whenever you look into the solar panel details, whatever we are taken, V1 is 10, V2 is 20, V3 is 50, V4 is 100. Solar panel is VOC is 33.624, ISC is 7.213, power is 167.6, peak is 27.193 volts, high peak is 6.163, fill factor is 69.1%. So this is the thing. Now I'll end this session. Thank you for patience listening, and you can ask me some doubts. Thank you.
Sir, with your permission, should I ask the participants
Please,
to
please.
raise their doubts in chat box?
Please.
So all the participants are requested to pose your doubts in chat box. Then we'll share the doubts to the respected speaker of today's session, Dr. Rajagopal.
Okay.
Please raise the doubts.
Somebody was raising hand and all.
If anyone raising hand, we'll try to unmute them, sir. You can we can have verbal.
Okay. Please, let them ask. Screen not visible is visible.
Sir, everything is visible, sir.
Okay.
Participants are requested to raise your doubts by posing a question in the chat box, or you can raise a hand. We'll try to unmute you. Then you can have a direct interaction with the speaker.
Oh, okay. Have you understood my session or not? There is no doubt at all. Okay. Anybody is having doubt, they can ask. If not, we'll end this session.
Thank you, sir. Thank you for your valuable session, and we feel pride to have you here with for today's session, sir. Now, with huge respect, I will try to hand over the vote of thanks to convener of FDP, Malkarin Reddy, sir, head of the Department of EEE, Balaji Institute of Technology and Science. Sir, over to you.
Okay, thank you, Sridhar. Respected Dr. Rajagopal, sir, and all the participants. It's my privilege to have been asked to propose a vote of thanks on this 1 week FDP. Thank you, sir, for your illuminating presentation on today's topic, solar power with reduced switch multi-level inverter. We hope that your support will be there in same way in future, sir. Once again, I thank you, sir, for sparing your precious time for all of us, sir. Thank you so much, sir.
Thank you.
Thank you very much, sir.
Okay. See, sir, this is T-type inverter is better than multi-level inverter for PV grid. See, there are many types of inverters which are coming into picture. Priyanka, reply from to everyone. Okay. No. See, our idea is what? Whichever the inverter you use, there should be less disadvantages. And PV grid interface, the previous, whenever you are interfacing with the grid, the big problem comes is water. There should be no voltage and frequency changes between the grid and the frequency. So for that, the D-STATCOM model is a well also appreciated model. And here also, I don't know whether we can pump directly into the grid, because we have to monitor the frequency and voltage all the time. And if any change in voltage and frequency, what happens, the power will flow from the grid towards the solar panel, which may damage the solar panel. And the second one is what? For installations of 700 watts per minute, how to calculate the power density networks, and fill factor is constant, but just 1 minute, what is VOC and ISC, but not VOC and ISC. See here, we have to model a single diode model. We cannot do calculations. See, these are the dynamics basically. Two diode model is also available for solar panels. Single diode model we by say running of the things, what we have done is single diode model. So whatever the power density, whatever your calculation you are doing, by taking a single diode model, making a panel, then calculating the power density. To understand the power density in networks, this NKT is what networks.
Sir, another doubt posed by Mr. Panda: how to reduce spikes of voltage and currents in multi-level inverter?
See, whatever the um, spikes, whatever you're seeing in multi-level inverter, see what is calculate the performances to calculate the any. What is a performance indices to be calculated for a multi-level to show advantage. See, first thing is whatever the results I'm showing, I have not manipulated any results. It is an theoretical results, simulated results, and hardware results in one of the NIT. There is no spikes in our waveforms. The THD is 1%. Just you can imagine how it is with the 10 switches we are able to operate to a 31 level, and getting a THD less than one, equal to 1% is. I'm working on power quality from last 10 years. 10 or 12 years I'm working on power quality. To reduce the THD less than 5% is the biggest task in hardware implementation. But here in this particular case, we got the THD is only 1%. And thank you.
Another
See,
doubt posed by Murli Krishna:
yes.
MPP will have any variation with geometrical location?
See, whether it is geometric, that's why MPPT is very good. Wherever you put the panel, my algorithm is going to look after the maximum power point. And maximum power point algorithm, whatever the panel you have, whichever the place you have. So here we are only operating at the maximum power point. That's the beauty of this algorithm. This is the beauty. Murli Krishna, B. Murli Krishna Garu is in Oman, I think. Is the same person?
Yeah. Yes.
Okay, he is my friend only. Okay. Murli Krishna Garu. This can be operated at any geographic location. Only sunlight should be available. What is the DC link? What about the DC link utilization of the inverter? See, solar power is always free, and we are saving in a battery only. I shown a battery only. We are not able to utilize the power, it is stored in the battery. So here, whenever we are implementing in this one, we have put a battery which is shown in the assembling model. Whenever we are doing hardware, we are used a battery things there, where the voltages and can be stored and can be put up. Can be code MPPT algorithm. You can do very simply in Simulink, very simply in Simulink M file also. Both are done in Simulink. Raja Satish Kumar Garu, I've done this one in Simulink. Basically, you can do in Simulink as well as M file. That's all.
Okay, sir. That's all. Thank you, sir. Thank you for spending your valuable time with us. Sir. Thank you.
Thank you,
very
sir.
much.
Thank you, Thomas.
Shall we wind up the session, sir?
Okay, sir.
Sridhar, sir.
Yeah, I will close the session. Thank you, sir.
Thank you, sir.